What is dark matter, and why are astronomers so confident that it exists? The answer to the first question, we don't know right now. But astronomers have built up evidence that something that has mass but no light exists and is pervasive in the universe. This evidence starts with the Milky Way. When we map out the mass motions of the galaxy, its disk, towards the outer extremities, we see continued high circular velocities, which have no explanation in terms of Newton's law and Kepler's laws of motion. Basically, the light in the galaxy is distributed far more centrally than the mass as indicated by the motions. There are only two alternative explanations. One is that our theory of gravity is simply wrong, and that would be Newton's theory of gravity. Astronomers have considered the possibility that Newtonian gravity is incorrect or needs to be altered on very large scales. And it's important to remember that Newtonian theory is only verified experimentally on solar system scales. So on much larger scales like hundreds or thousands or hundreds of thousands of light years, we don't have a direct experimental test of the theory. If the force law deviated from inverse square by only a few percent, you could explain away dark matter. But that's not a trivial thing to do. Newtonian gravity has passed every test put to it over hundreds of years, except in the situation of very strong gravity where we need Einstein's superior theory. On large scales and for weak gravity, we think Newton's theory is an excellent theory. Astronomers haven't come up with anything better, and they're loath to discard it. The alternative is that there is mass that doesn't emit light on large scales in our galaxy and also in every other galaxy and in the space between galaxies. Evidence for this has slowly and steadily accumulated over 4 decades to the point where dark matter is now part of the furniture of extragalactic astronomy. Astronomers simply believe that it exists, and they're trying to find ways of understanding its physical nature. Let's look in a little more detail at how astronomers reach this conclusion for our galaxy in particular, but any spiral galaxy. One of the figures of merit of a galaxy is its mass-to-light ratio, the ratio of its stellar mass to its stellar luminosity. Because we understand well how stars evolve, the mean mass-to-light ratio of a stellar population is a well-determined number. What we see in our galaxy is that the mass-to-light ratio of the disk of the galaxy is much larger than can be explained by any simple stellar population. In terms of mass-to-light ratio, the mass-to-light ratio of normal stellar populations is higher than the value 1 that it would have for the Sun, because so many stars are dim dwarf stars. Typical mass-to-light ratios for old stellar populations are between 5 and 10. The calculated mass-to-light ratio for the Milky Way and other spiral galaxies is almost 10 times larger. If we want to estimate the mass of our galaxy, we simply apply Kepler's law. And we can do this very robustly for the mass within the solar orbit. Remember that the Sun orbits the disk of the galaxy about 2/3 of the way out to the visible edge of the galaxy. Using Kepler's law, the stellar mass interior to this orbit is about 2 times 10 to the 11 solar masses. 200 billion times the mass of the Sun. But the entire mass of the galaxy seems to be 10 times larger, 2 trillion solar masses. And most of that mass is inferred to be at larger scales than the Sun's orbit, so distributed to the periphery of the galaxy, even beyond its visible edge. When we're modeling the motions of galaxies, the indication for dark matter is not any subtle or small effect at the 5 or 10% level. It's dramatic. As you map the rotation speed of a galaxy out beyond the solar radius to the edge of the visible galaxy, and using gas clouds and diffuse stars, you can go even beyond. Remember, galaxies don't have sharp edges, so there are tracers of the mass motions beyond where we'd see the visible edge. If you do this, the dichotomy is stark. The rotation speeds predicted by Kepler's laws should have declined by factors of 3 or 4, moving beyond the visible edge. In fact, they're constant to the visible edge and even beyond into the thin gruel of intergalactic space. So this factor of disagreement is very large and cannot be easily explained away by experimental error. But rotation curves are not the only reason astronomers think dark matter exists. Other evidence has come from the exquisite imaging of the Hubble Space Telescope or other ground-based observatories able to make very sharp images of galaxies. Einstein's theory of gravity says that mass bends or deflects light, and the overall distribution of galaxies in the universe and the mass associated with them, deflects light traveling through the universe. Think of the universe as a funhouse mirror with slight undulations caused by mass distributions that deviate light as it passes, subtly distorting images. This effect can be easily measured with large telescopes. It's quite subtle, just a few tenths of a percent deviation of the average shape of a galaxy caused by mass deflections along the way. But the sum of those deflections is another affirmation that some dark material exists not only within those galaxies, but in the space between them. Beautiful evidence that dark matter, or something like it, exists has come recently from observations of the great observatories, the Hubble Space Telescope and the Chandra X-ray Observatory. There are several situations in the distant universe, a few hundred million light years away, where two clusters have approached each other and passed through each other. The distance between galaxies is such that when clusters approach and pass through each other, the galaxies rarely collide. They simply interact by gravity and then continue on their way. However, there is hot gas in a cluster, and the gas is viscous, and so the gas belonging to two clusters heats up and emits X-rays and crashes into one pile. In at least two clusters, we've been able to observe the pileup of gas that emits X-rays, while the dark matter has continued and sailed on through in each of the clusters. The dark matter is measured by the gravitational lensing effect I just referred to. In these cases, it's excellent evidence that something like dark matter, which interacts extremely weakly with electromagnetic radiation, exists and forms most of the mass of each of these clusters. There's another reason that astronomers are fairly confident that dark matter exists, and it's based on theory and simulation. As computers have grown in their capabilities, we've been able to simulate larger and larger volumes of the universe. In particular, how, starting from smooth initial conditions, the clusters and galaxies could have formed in the first place, by simple gravitational effects. If, in a computer simulation, you fail to put in dark matter as an ingredient at the beginning of the simulation, you fail to produce anything that looks like the real universe we live in. Basically, the matter will crunch down onto small scales and produce too much structure early on. Dark matter mediates the formation of galaxies and clusters and produces the delicate filamentary structure of clustering that we observe in the actual universe. So without dark matter as an ingredient in the simulation fails to describe what we see, which is a reason that theorists are confident that dark matter exists. So we have fairly impressive evidence that some form of matter that interacts very weakly with electromagnetic radiation and exceeds the visible mass in the stars and all the galaxies exists. But what is it? So far, astronomers have only been able to play the game of elimination, ruling things out. We can think of a detective mystery where in the final scene, all the possible killers in the stately home are gathered together, and one by one their alibis are inspected and they're ruled out of deliberation, and we find out who the final culprit was. Well, the game doesn't work that neatly in science. We may not be able to think of all the possibilities, but the number that have been ruled out is actually quite impressive. Let's start at the high end. What about black holes? Black holes, of course, by definition, are black if they're truly isolated in space. Perhaps the universe and galaxies are riddled with black holes, and that's the dark matter. That's actually very easy to rule out. Imagine that there was a party in your house, teenagers left alone over the weekend. You may not have been there for the party, but you'll sure see the damage they left behind. Well, anytime a black hole forms, there was a party beforehand in the form of a supernova, a violent explosion, ejecting gas, causing high energy emission, emitting X-rays in a supernova remnant for millennia afterwards. So it's impossible to form black holes without seeing evidence of the violence that preceded them as a massive star dies. And to have enough black holes in the universe to account for dark matter, you'd have to have vast numbers of massive stars dying at some point through history. We see no evidence of that. So stellar mass black holes are actually the easiest things to rule out for dark matter. The next possibility is interesting. Recall that as you go down the mass spectrum of collapsing gas clouds, there's a mass corresponding to 8% of the mass of the Sun, below which a star does not form. The gas cloud simply becomes hot, but never hot enough for fusion to occur. Nature will probably collapse gas clouds that are less than that number. They may be 5% the mass of the Sun, 1%, 0.1%. And so, in theory, there's a set of collapsed objects out there that are warm but not radiating by fusion. And if they're small, they might actually be quite dark and not visible in light. These have been called massive compact halo objects. If the halo of our galaxy was filled with them, they could account for the dark matter. We already have an indication that there are many more low-mass stars than high-mass stars, so it's reasonable to hypothesize an extremely large number of substellar objects, ranging down to Jupiters and even below, existing in free space. Think of them as free-floating planets, if you like. This is harder to rule out, but lensing, the effect where mass bends light, has actually done so. Experiments in the mid to late 1980s looked for gravitational lensing taking place throughout the halo of our galaxy in terms of the momentary amplification of the light of a background star from a foreground star. That same amplification could occur if the foreground object was a massive compact halo object, a substellar object or a Jupiter, for example. The statistics of that search were very impressive, and they easily ruled out the halo being composed primarily of such objects. Machos, as they're called, may exist, but they don't form the majority of the dark matter. With normal stars, such as red dwarfs, and the remnants of massive stars ruled out, and also substellar objects, the last possibility is even smaller physical objects, say asteroid size, ranging down to house size or even down to dust grain size. In the interstellar medium and in the space between planets, there are of course a lot of rocks, and those rocks only emit infrared radiation. Perhaps space is filled with such dust or particles. It turns out this was ruled out 20 or 25 years ago by the IRAS satellite of NASA, which looked across the sky at far infrared wavelengths. Even if you hypothesize that space is filled with tiny particles or boulders or house-sized objects or asteroids, those objects do not exist in isolation from radiation. They're radiated by the light from nearby stars or galaxies, and they reach an equilibrium temperature sufficient to pump out infrared radiation. IRAS was a sensitive mission that would have seen the diffuse dim glow of far infrared radiation from such hypothetical objects. They simply don't exist. Also, that large an amount of dust in interstellar space would dim and redden the light of distant galaxies in a way that we simply don't observe. If we summarize this, astronomers have essentially ruled out dark objects ranging from black holes down to dust grains 1 micron in size. All that's left is the only current viable explanation for dark matter, a subatomic particle. So we're left with one viable explanation in physics or astrophysics for dark matter, a subatomic and fundamental particle. Remember the constraints. This particle has to dominate the number of normal particles, protons, neutrons, and electrons, by a factor of several. So it's a ubiquitous particle. It has to interact very weakly with electromagnetic radiation, which puts a strong constraint on the type of particle it might be. In general, these particles are called weakly interacting massive particles, WIMPs, the acronym. We think that that's what the dark matter is, but no such particle has yet been detected, although searches are underway. What kind of particle might this be, even in principle? Physicists are aware that the standard model of particle physics is incomplete. One of the favorite extensions of the standard model of particle physics is called supersymmetry, where the fermions, particles with half-integer spin, and bosons, particles with integer spin, which have quite different properties in the laboratory, are actually unified in a sense by a range of shadow particles for each of them. This of course doubles the number of particles, because each fermion has a supersymmetric twin and each boson has a supersymmetric twin. For these to be unobservable currently, these would have to be high mass particles only available at very high energies, perhaps beyond our current accelerators. So this is speculative theorizing that unifies physics in an interesting way, but produces effects that are difficult to observe in the laboratory. It turns out that high-energy physicists, such as at the Large Hadron Collider at CERN, are actively looking for the lightest supersymmetric particles. And the lightest of them, or the least massive of them, could indeed have the properties such as to be dark matter. This is an exciting convergence between a desire of physics to explain physics beyond the standard model, and astronomers to explain one of their biggest enigmas. Unfortunately, supersymmetry is not one theory, it's a suite of theories. And with very little experimental guidance, it's been hard to discriminate between these theories. The slightly disappointing news from CERN in the last year or so is that hints of supersymmetry have not been seen in the LHC running at its highest energies. And this has already ruled out some of the simplest and most attractive supersymmetry theories. So although supersymmetry is desired by physicists and would provide a neat potential explanation of dark matter for astronomers, there's no verification of this theory at present. Dark matter remains an enigma. High-energy physics is trying to find supersymmetric particles by high-energy collisions, but there are other ways to find dark matter. So there's another set of lab experiments designed specifically to detect a weakly interacting massive particle, or WIMP. Most of these are situated deep down mine shafts because the major contaminating noise for any search for dark matter particles is interactions of cosmic ray with the detector. The detectors in these cases are usually large, ultra-pure lumps of solid-state material such as silicon or germanium. A series of these experiments is underway where the shielded detector, shielded from cosmic rays and other interfering particles, is simply observed carefully for a long period of time for the very occasional interaction of the detector particles with a passing dark matter particle. The weak interaction strength of the dark matter particle means that a large mass of detector, ultra-pure, has to be observed essentially for years to find sufficient interactions. Current experiments are in a regime where in 3 to 5 years they should detect dark matter particles if they are indeed weakly interacting massive particles, the kind predicted by supersymmetry. At the moment it's tantalizing. No detections have been made, and within a couple of years, if the detectors still find nothing, then we'll be back to square one. Most of the supersymmetric theories, or plausible explanations of dark matter from particle physics, will have been ruled out. The evidence for dark matter is convincing. Based initially on rotation curves of spiral galaxies, it's been found in essentially every spiral and elliptical galaxy inspected, even down to dwarf galaxies. Additional evidence comes from gravitational lensing, which shows that dark matter not only exists in halos around galaxies, but it permeates intergalactic space. As for what dark matter is, so far we've eliminated everything from black holes down to small dust grains in space. The only remaining viable option is a subatomic fundamental particle, as yet unobserved in the physics lab or with accelerators, and representing an extension to the standard model of particle physics. The answer may be within a couple of years based on lab and accelerator experiments as to whether this dark matter particle actually exists.